Your skeletal system is a structural framework that gives you body shape and provides protection for internal organs and soft tissues. It's a hard shell. Skeleton is derived from the Greek word meaning dried, because if you think about it, if there was a cow out in a field and it died during the winter, what they would find, what was left, was the bones. It is a dynamic living tissue that's capable of growth, adaptation to stress, and undergoing repair after injury. A lot of people think the skeleton is just something that sits there, but in reality, if you break a bone, it repairs itself. It's constantly changing. It's constantly, basically, it's a living thing. So there are 4 components to your skeletal system. Most people think bones, which is correct, but you also have to include things like the cartilage, the tendons, which are the things that hold the muscle to the bones, and the ligaments, which are the things that hold the bones together. So the functions of the skeletal system. You've got support. Bone is very rigid, it's very strong, it's well suited for bearing weight and a major supporting tissue for the body. Cartilage is also firm. It is flexible support, but it still is support. Your nose is the shape it is because of the cartilage that puts it together. Ligaments are actually strong bands of fibrous connective tissue that hold the bones together. That's why when you're walking, your hip doesn't just dislocate. Protection. This is pretty obvious. It's a hard shell that surrounds your soft organs. Movement. Now I know you're going, wait a minute, muscles are the only thing that move. And while that's true, our joints where our bones come together are pivot points so that the muscles can use them as a pulley system. So this is another reason why we include things like tendons and cartilage as part of the skeletal system. Storage. Our bones are made out of something called calcium phosphate. So when we lived in the ocean, it was pretty easy to get any minerals we needed out of the water. But as we evolved and became land-dwelling animals, we kind of had to have a storage facility for the calcium and the phosphate that we needed. Our bones became that. Our bones, the hard part of our bones, is made out of calcium phosphate. Yellow bone marrow is stored in the long bones, and it's a storage site for fat tissue or for lipids. Basically, we can extract that for for energy if we need it. 5, blood cell production. I'm sure most people have heard of red bone marrow. Red bone marrow gives rise to all blood cells, white blood cells, neutrophils, thrombocytes, leukocytes, all of them. And the platelets. So cartilage. There are 3 types of cartilage: elastic, fibrocartilage, and hyaline cartilage, but the one we talk about that's most closely associated with our skeletal system is the hyaline cartilage. Most bones develop from it. Bone growth and length is dependent on hyaline cartilage, and repair involves hyaline cartilage. Chondroblast. Remember, blast means to build. Chondro means cartilage. Okay. Chondroblasts are responsible for producing the matrix that the cartilage cells sit in, and they basically start building matrix around themselves until they are completely surrounded by matrix. They trap themselves in a little cell where they're sitting. When they are trapped, they evolve into something called a chondrocyte. This is the mature cell that's left occupying that little cell I talked about called the lacuna. Lacuna in Spanish means cradle, so it's cradling the cell, it's holding the cell. The matrix of hyaline cartilage contains collagen. Collagen is the lanyard. It's flexible, but it's strong. And proteoglycans. Proteoglycans are kind of like a water balloon. You can push them, but then they pop back out. They hold their shape really well. The perichondrium. Peri means around, chondro means cartilage. The perichondrium is a double-layer connective tissue sheath or covering that covers most cartilage. It is lined with blood vessels and nerves. So if you got your cartilage here, this is here, okay, this is the perichondrium. In between there, you've got blood vessels and you've got nerves, okay? So if I want anything to get from, if If I want anything to get from the blood vessels and nerves here into my cells inside of here, it actually has to rely on diffusion, going from high to low concentration. I don't have any direct blood vessels inside of my cartilage, but the matrix is soft enough that things will actually move through it. Now, articular cartilage. So if I have a bone, let's say I have a chicken leg, everybody knows that on the outside of that, you've got this kind of cartilage cap, right? We've all had a chicken leg and we've all pulled that off. That is called the articular cartilage. When two bones come together and they've got kind of the meeting where they meet, that is called an articulation. So when we have the cartilage on the caps, that's actually to protect the ends of the bones. Bone has a consistency of fine grit sandpaper. Having fine grit sandpaper rub on fine grit sandpaper isn't a good sensation. Having cartilage at the ends, the cartilage is fairly smooth, so it makes the movement of our bones, it makes it a lot smoother. It makes it glide instead of grinding. Cartilage grows in two ways, appositional growth and interstitial growth. Now, the two words themselves will always mean the same thing. Appositional means that you've got growth on top of something that's already existing. So with cartilage, we grow on top of existing cartilage. Interstitial means in between the tissue. So chondrocytes within the tissue divide and add more matrix between existing cells. So here I've got something that's already established and I start growing on top of it. Here I've got new growth kind of in the middle of everything instead of on the top. Now remember, appositional and interstitial will always mean the same thing. So, switching gears, talking bone. The bone matrix is responsible for the major functional characteristics of bone. It's described as reinforced concrete. So if you think about a concrete slab, okay, when they pour that concrete slab, they normally don't just pour concrete. They put something called rebar. It looks like metal webbing almost, and then they pour the concrete on top of it. Now, they do this for a really specific reason. They do this because the concrete itself will just start to kind of crumble away if it doesn't have anything to hold on to. Putting the rebar there actually gives it something to pull against and gives it a slight amount of flexibility. Let's say the weather changes, it goes from being really cold to really hot. You don't want that concrete without something that will expand and contract like that metal, kind of giving it a little bit of flexibility. So for our bones, we have two parts, the organic material and the inorganic material. The organic material is going to be the rebar. Okay, so it's going to be this kind of grid-looking metal. We've got collagen. Remember, collagen is the lanyard. It's flexible, but it's strong. And we have the proteoglycans. Proteoglycans are the water balloons that if you poke them, they pop back out. The inorganic material, though, is the concrete. Okay, so this is what gives your bones their hardness. This is what actually gives your bones the ability to bear your weight without bending or bowing. Hydroxyapatite, which is a very fancy way of saying calcium phosphate, is the inorganic material we have in our bones that help to give us our weight bearing. So here's a bone that has both, okay, at the top picture. If I were to take out all of the concrete or the hydroxyapatite, your bones would kind of look like this. They would have the flexibility, but they wouldn't have the ability to bear weight. If I were to take out all of the collagen and organic matter, this is what the bones would look like. They would have no flexibility to them, so if you were to hit the bone, it would shatter like a fishbowl. I'm not going to worry about that for now. We're not going to worry about this. Well, not that. Osteoblasts. So bone cells, you have to remember bone matrix is really hard, which means that you can't really diffuse anything through it. If I had a wall of concrete, it's not like if I pour water on one side, the other side would get wet. It doesn't work that way. So when I first make bone, I actually place, I'm going to switch the laser pointer, I place all of these cells in place that are osteoblast. Remember, blast means to build. And as they start to put matrix down, they're surrounding themselves. But notice that they're still connected to each other. You can see the connections between the cells. As they mature and as this matrix starts to get hard like concrete, these cells are basically trapped, kind of like the cartilage cells in a lacuna, in a cradle, but they're connected to each other, which kind of gives them a little bit of an advantage. When they're surrounded and they're trapped, they become osteocytes. Basically, they are going to be mature cells at this point. So the cell connections are important because let's say that I have a blood vessel here. Everybody knows about the osteons and those central canals in the middle. This cell can then get nutrients and share with their neighbors through these cell-to-cell connections. By the same token, if I have a waste product over here, then I can basically transport that waste product over until I get to a blood vessel where I can drop it off. Now the osteoclast, remember clast, you can think of the word crush or breakdown. Okay? If I break a bone and I've got bone fragments everywhere, I've got to clean that up before I can repair it. Osteoclasts are responsible for dissolving that bone matrix. Now, you don't have a picture of osteoclasts here, just so you're aware. So this is just what I went through. Osteoblasts produce collagen and proteoglycans. They become the bony matrix connecting to each other via cell processes, which you can see in the picture. And they produce matrix vesicles. Don't worry about that for now. That's not important. Ossification is a very fancy way of basically saying bone growth. I'm actually turning that matrix, that kind of semi-soft matrix, into something harder, the concrete. The osteocytes are the ones that occupy that space. They are basically taking care of the day-to-day. They take care of the bone. They repair if there needs to be repair. They share, like I showed you in the last picture. The osteoclasts kind of remind me of scrubbing bubbles from the commercials, but they're responsible for bone resorption. Yes, I know, it just means reabsorption. Don't ask. I don't know why they use another word. The ruffled border makes contact. You can see that here and here, and basically seals it down almost like a suction cup. The thing about how these osteoclasts work is they basically put acid on top of the bone matrix until it dissolves. Acid doesn't know friend from foe. Acid will just eat whatever it comes into contact with. By suctioning themselves down and isolating where they're releasing the acid, it means the acid doesn't float everywhere away from here. It basically stays in place, which is what we want. So once this stuff down here has been dissolved, I actually have to take this back up into my cell and process before I can let it out on the other end. If there's still acid there, I don't want to just let that willy-nilly out into my body. Now, why would I want to dissolve bone matrix? If I need calcium, if for some reason I haven't had calcium in my body in a really long time, I can dissolve the bone matrix to replace that. I've said this before quite a few times. Calcium is very important. I have to have high levels of calcium in my body for my body to function properly. Woven versus lamellar bone. Okay, woven bone is like a rough draft. If you think about collagen fibers just kind of being dropped down, I think of silly string. Woven bone is the rough draft that gets put down during repair of a fracture, during fetal development. Something you have to understand about bone, unlike other organs in your body, bone always has to have a template to follow. So woven bone is kind of like that first rough draft template, but then it gets replaced with lamellar bone. Now, you are familiar with lamellar bone because of lab. You know that you've got the osteons with those circles, right? The lamellar bone is basically arranged so that the collagen fibers are arranged parallel to one another. They're actually designed so that if I were to put weight on this, I've got these columns of collagen to hold that weight, to bear that weight. Bone remodeling is just like house remodeling. Basically, we're removing something old and we're adding new. The only difference is that we're adding new bone and removing old bone. Spongy bone versus compact bone. If you look, give me a second. Let me use green. If you look here, you can see that this bone on the outside is very dense. There's very few spaces there. But if you look here, this looks like bread. That's the spongy bone. It has a lot of space in it and usually is filled with bone marrow and blood vessels that kind of weave their way in and out of those spaces. The compact bone is the one that we see in those big bone models. It's very dense. You do have cells in it. There are central canals and perforating canals, but for the most part, it's just solid bone. Spongy bone has a lot of spaces in it. You can see that right here in this blown up picture. The lamellae combine to form trabeculae. So you've got the pores in a sponge, the holes in the sponge, but these solid portions that you see here, okay, that I'm coloring in, these are called trabeculae, okay? Now, something that's kind of interesting, I think people think that this looks completely random, but if you actually take a section of this and blow it up and you look at it under a microscope, you still have those lamellae that we talked about in the compact bone. This is not as random as you think. All of these lines that you see that look random are actually very intentionally made with the idea that if I lean to the right or lean to the left or lean forward or lean back, I still have pillars of bone to hold my weight. The compact bone. This probably looks familiar. It probably looks like something you've seen in the lab with my lamella and my central canals and my osteons. I'm going to sneeze. I'm sorry. Anyway, so compact bone is called compact because it's dense with very few spaces. They are organized into lamella. You've got the concentric lamella, which look like a bullseye. You've got the circumferential, which go all the way around the circumference of the bone, and you've got the interstitial. Now remember what I said about interstitial, always means the same thing, in between the tissue. If I've got pipes stacked up, there are always little spaces in the middle of those pipes because they're not squares. Those spaces have to also be filled up with bone tissue. Concentrics surround a central canal, which you can see in the picture here and here. The interstitial are remnants of bone remodeling, and you've got canals in these bones. You have to remember that what I said before, this is like concrete. Nothing is going to go through it. So I have to have ways of connecting cells to cells, cells to blood vessels to cells, and that includes perforating canals and central canals so that these cells can share with each other. Bone anatomy. You've got long bones. You've got short bones. Long bones are longer than they are wide. Short bones are about the same height as width. You've got flat bones. Now, flat doesn't necessarily mean I'm flat like a, desktop. They are just very thin. The parietal bone of the skull technically is considered a flat bone, even though it's curved. But think about its shape. It is very much flat. It's just like having a piece of paper that you've kind of curved over. Still a flat sheet of paper. Irregular bones, well, they look weird. They don't have a long bone or a short bone or a flat bone arrangement to them. So they're called irregular.